the exam day, there's a conflict for many of you actually who are taking 무슨 수업이었죠? 공학생물 수업 듣는 분들이 conflict가 있어서 1분반 유동원 교수님 분반과 협의한 끝에 저희가 합의에 도달한 날짜가 다음 것 같습니다. 4월 26일 그리고 6월 14일 중간 기말고사로 제한 드리는 날짜입니다. Okay, so this is the modified exam date, April 26th, and for the final June 14, Saturdays. Any conflict? conflict 있는 사람? 토요일 날이에요. 토요일. From 10 a.m. to 12:30 p.m. Is that okay? Or all of you? 지금 이야기해야 돼? 못 바꿔. 다 돼요? Okay, seems like this is the fixed schedule for midterm and final. Okay, again, April 26th, Saturday for the midterm, and June 14th for the final. Okay, those are Saturdays. And accordingly, the schedule for this course is slightly changed. So you can refer to this table, not the table in lecture 0's file. Okay. And again, the blue highlighted one, this will be substituted by the recorded lectures. Okay. Any questions? All right. If not, then let's get into the lecture 1. Okay. And last time we discussed why carbon is so special. Right? Why there are so many carbon-containing compounds. And simple intuitive answer for that is the location of carbon in the periodic table can answer those questions. Right? If you think about the carbon's position in the periodic table, you can rationalize this element can neither readily give up nor readily accept the electron. What does that mean? Basically, carbon can share electron to make a bond with the other elements pretty well, right? That's why carbon can formulate millions of compounds with wide range of chemical properties by sharing electron with other elements. Okay? That's why carbon is a special and central element in organic compound and organic reaction. Okay? All right, so where we are, this is a second lecture. And you are going to discuss basically the Gen Chem stuff, the general chemistry stuff. I'm pretty sure you guys are all familiar with the topics that we are covering out for today, the structure and bonding within the organic molecules, organic compound. And today's lecture will cover up the stuff in chapter 1 of the textbook. Okay? And probably cannot finish chapter 1 stuff today. We'll continue to discuss the remnant part on Wednesday, and we're getting into the next chapter, the acid-base chemistry. All right, so today's topics, keywords, we're going to review. Again, all the topic we'll study for today is basically the general chemistry stuff. So we'll review what is the atomic number, mass number, isotope, atomic weight, molecular weight, blah, blah, blah. And we'll discuss the electron distribution within an atom and what the weight function means, what orbitals means, and the general principle, how electron occupy within the atomic orbitals, the opt-out principle, Pauli exclusion principle, and Hund's rule. This is all basic stuff, but very important and applies to the organic molecules in bonding or atomic orbitals that encompass the element in organic compound. Okay? And then we'll review what is covalent bonding, Lewis theory, octet-rule, and discuss the formalism, how to describe the structure of the organic molecule. The structures, pretty sure you all know about Lewis structure, calculus structure, content structure, skeletal structures. So it's quite useful for describing the structure of the organic compound. Okay? And probably we'll continue to discuss the molecular orbitals and hybridized orbitals and how to describe the bonding nature with this orbital formalism. Okay? Again, today's topics are not that complex and not that hard. It's all Gen Chem stuff. Right, structure of an atom. This is how atom looks like. You have nucleus and electrons and neutrons. Right? So negative charged electron. And you also have the positively charged proton. Top of that, you may have the neutral neutrons. Right? And what is the atomic number? The numbers indicate the number of proton in its nucleus. Okay? The mass number refers to the sum, okay? Summation of the proton and neutrons. Okay? But you can ignore basically the mass of the electron because the mass of the electron is very, very small as compared to the mass of the proton and neutron. Okay? So for the mass number of a given atom, you can only refer to the number of proton and neutrons. Okay? So here's an example for carbon. Right? Atomic number of 6, and you can also refer to the mass. So from this number, you can count how many neutrons exist in this element. Okay. So in the nucleus again, you have protons and neutrons, which define the mass number, and the surrounding electron very, very light, so you can ignore its weight. What is isotope? Isotope species having the same atomic number, but having different mass numbers. Okay, so this is a series of isotopes you can identify, right, for carbon. And these isotopes, they all have the same and common atomic number, which is 6. From which you can guess, right, what is the number of neutrons for each case. The isotope have obviously having different mass number, so you can guess like 6, 7, and 8 neutrons for each case respectively, right, for these isotopes. Okay. Atomic weight, this is the average weighted mass of a given atom. Right? So for instance, you can provide, right, the atomic weight of carbon, given that the 12 carbon and 13 carbon has this much of the weight and the relative population, okay, for each case respectively. And then you can do simple calculation, simple mathematics. Okay. So multiple of this and also multiple of this can be summed up. Right? Basically, your average out, right, the atomic weight of a major isotope for a given atom. Right? That will give you the atomic weight. Okay? Then what is the molecular weight? You can repeat all the processes, right? You can do the same thing for all the elements, right? And get the average number, right? The sum of the atomic weight of all the atoms in the molecule. Right? That will give you the molecular weight. 쉽죠? 다 일반화학 시간 때 배운 겁니다. 기억 안 나시는 분들은 한번 리뷰를 하세요. And this is a simple page, and answers are all given below. Right? So you can just practice yourself. Oxygen is 3 isotopes, right? 16, 17, and 18. You can the number of proton and number of neutron, right? And again, following the definition, you can get all the numbers that you need. You can also try to calculate the average weight, right? Fluorine has two major isotopes, right? 35 and 37. For each, you have a given relative population. Right? From this, you can answer, right? With this question. 그래서 뭐 어려운 건 아니니까 한번 복습을 해보시기 바랍니다. Right, what about distribution of the electron in an atom? There is a rule, right? And this is again the Gen Chem stuff. For those who forget this fundamental concept, you guys should review this this part. So electron in an atom can be thought of as occupying set of the concentric cells that surround atom's nucleus. The closest shell, the nucleus called the K shell, the first shell, right? Followed by the second shell, just L shell. Then the third shell, just N shell. And so farther and farther from the nucleus. The first shell, for your information, is called N shell. Right? And for each shell, they're just the corresponding atomic orbitals, AEOs, right? Or we can sometimes call the subshells, right? The subshells corresponds to the atomic orbitals. Okay, so K shell has one S orbital. And L shell, the second shell, has S and P orbitals, right? And maybe you can put 2 in front of S and P for the second shell, right? We can call 2S and 2P orbitals. These are subshells for the corresponding, right, primary shell. And for the third shell, you have S, P, and D orbitals, or subshells, or you can call out 3S, 3P, and 3D orbitals. They belong to the third shell. For the fourth shell, you have additional orbital, the F orbitals, right? So you have S, P, D, and F orbitals in Bird's shell or N shells. And these are a number of the atomic orbitals. For 1s orbital, you only have a single orbital, right? For 2s and 2p orbitals, you have 1 and 3 orbitals respectively. And for s, p, d, or 3s, 3p, and 3 orbitals, you have 1, 3, and 5 orbitals respectively. Okay. For f orbitals in 4th shell or n shell, you have 7 numbers of orbitals. Okay. The bottom line represents the maximum number of electrons, right? Which follows the following equation, by the way: 2 times n squared, and n here meaning the principal quantum numbers. For the K shell, should have mentioned this earlier. N equals 1. For the L shell, n corresponds to 2. Okay? And for the M shell, n equals 3. For N shell, n equals 4. Okay? So if you apply n equals 1 into this equation, you can rationalize the maximum number of electrons in this shell, right? And for the second shell, 2 times 2 squared will give you 8. 2 times 3 squared will give you 18. 2 times 4 squared will give you 32. Okay? And this is the maximum number of electrons. Right? And here's a summary. Shell can contain only a fixed number of electrons. The first shell can hold up to 2 electrons, right, as we discussed. And the second shell can hold up to 8. Third shell can hold up to 18, and so forth. Okay? And again, 2 times n squared, that's the general formula for the maximum number of electrons. Okay? 다 배운 거죠? 그죠? And this is a cartoon illustrating the distribution of electrons within an atom again. You have the nucleus, and distribution of the electron, right? In each shell, right, you have the first shell, second shell, third shell, and fourth shell. In other words, K shell, L shell, right, M shell, and N shell, respectively. And from left to right, of course, the atomic orbitals experience increase in energy. In other words, right, the atomic orbitals closer to the nucleus have the lower energy. Think about the electrostatics. You can simply rationalize that this should be the case. And each subshell corresponds to an atomic orbitals again, right? So within K shell, you have one s orbital, the subshell, in other words. And for the second shell, you have s and p orbitals. These are subshells or atomic orbitals. For M shell, right? You have s, p, and d subshells. In other words, the atomic orbitals. Okay. And this is how the orbital looks like. And graphically, you can rationalize perhaps why s orbital should look like a ball, right? But for the scope of this class, you don't need to solve all the wave function, right? You can just accept, right, why s orbital looks like this. It can be rationalized if you solve the wave function. And this is a p orbitals, right? You have px, right? pg and py orbitals, and you have 5 degenerate d orbitals, right? And you have 7 degenerate f orbitals. You don't need to know, right, how f orbitals looks like. But for those curious about the structure of f orbitals, you can refer to this graphic, or after pictures you can find, or the text. Okay. All right. What is the ground state electronic configuration? Right. So basically, the ground state electronic configuration is the most stable electronic distribution or configuration you can think of. It's describe the atomic orbitals occupied by electron when they are all in the orbital orbital with the lowest energy. Okay? So 가장 안전한 상태에 있는 전자의 배치 구조라고 생각하면 되겠죠. And here's a table, right, showing you some typical examples of the electronic configuration of the smallest atoms from hydrogen to sodium. Okay? And of course, you have the atom numbers, or the corresponding case for hydrogen 1 and sodium for 11, right? And this is how, right, electron occupy the subshells and shells, right, from 1s to 3s. Okay. And you can notice the arrow, right? And each arrow indicate one electron, right? So hydrogen, you have unpaired 1 electron. For helium, right, you have the paired 1s 2 electrons, right? And this can go on and on. For the lithium, you have 1s electron in orbital, right? And 1 unpaired 2s electron, right? You can do the same thing for the following element, right? And there are rules and principles, right, for filling the electron within the atoms, the subshells. The first one is called the Aufbau principle. Aufbau here meaning the building up. Right? So this is quite straightforward name. So electron always goes to the available orbital with the lowest energy. That's what the Aufbau principle means or explains, right? And this is the energetic ordering of the subshells or orbitals. 1s, the lowest energy, followed by 2s, 2p, 3s, 3p, and 3d orbitals, for instance, right? So right hand side, the orbitals having higher energy than the orbitals on the left hand side, right? That means the left hand side orbitals has to occupy first, right? Or earlier than the orbitals in the right hand side, right? That's why you're occupying, right? 1s orbital first, followed by 2s orbitals, 2p, right? And 3s, 3p, and 3d, and so forth. Right? We'll discuss this part later on the next slide, which is about the Pauli exclusion principle. That's the Wundt rule. We'll discuss this first, right? The Pauli exclusion principle, you guys all know about this. No more than 2 electrons can occupy the same atomic orbital, right? In other words, one orbital can accommodate 2 electrons most, and these 2 electrons has to have 2 different spin, right? So the red box highlighted here, they'll have, right, the 2 electrons in one orbital set, right? And they have the opposite spin, right? And after filling up, right, this orbital set, you have to fill the next orbital, right? That's why the boron, for instance, with the atomic number 5 is 2 1s electron, 2 2s electron, and 1 2p electron. Okay. And what about this? That can be explained by the Wundt rule, right? What is Wundt rule? Wundt rule saying that the electron occupy empty degenerate before pairing up within one orbitals, right? That's why, right? For instance, for carbon, right? Instead of like filling up this orbital, you have to occupy the next orbital first, right? So electron occupy empty degenerate orbitals before pairing up in the same orbital. Okay? Same will apply to the nitrogen. So instead of like pairing up here or there, the third electron in 2p orbital will occupy here to maximize the unpaired electron. That's the Wundt rule. You guys all know about this. With all this principle and rules, you can perhaps define what is balanced and core electrons. The number of balanced electrons is very important. Right? Basically dictate and define the chemical behavior of a given element. That's why we care a lot about the balanced electron. Element in the same column, the periodic table, basically have similar chemical properties since they have the same balanced electron. So with this table, maybe we can distinguish what is the core electron and what is the balanced electron, right? Basically, the red boxed electrons are the core electron for a given element, right? For instance, the helium, right? You have 1s core electron. There's no balanced electron in this case, or maybe you can call out, right? These are all balanced electrons, but at the same time, it's core electrons, right? What about lithium? You have 1s core electron and 2s balanced electrons, right? What about oxygen? You have 1s, right, core electron, 2, right, core electron, and the balanced electron in blue boxed, right? 1, 2, 3, 4, 5, 6 balanced electrons from the oxygen. What about fluorine? Fluorine has 7 balanced electrons and 2 core electrons, of course, right? So again, balanced electron indicate the electron in an outermost shell. So the 2s and 2p electron in this case, right, sum up and formulate the balanced electron. Okay? And the 1s electron, the electron in the inner shell, they count up and formulate the core electrons. And this is a periodic table of the elements, right? And this is again Gen-Chem stuff, but you can distinguish, right, the number of the balanced electron in this periodic table and for the element in the same column basically have the same, right? Balanced electron does have same chemical properties. Right? So here you have the elements, series of elements having one balanced electron, two balanced electron, 3, 4, 5, 6, 7 balanced electrons, right? So they are and the commonalities in chemical properties, right? And maybe you can provide the ground state electronic configuration of this noble gas element, right? This is a basic one, so maybe you guys can try to review, get back to home, right? So basically you can refer to the periodic table, right? And then provide this ground state electronic configuration for each, right? And in this slide, right, the periodic table highlights the subshell, right? So you have 1s and 2s and 2p subshells, followed by 3s, 3p, right, 4s, and 3d, and 4p, right? So this is an exception, or the distinct point you need to remember, right? The electrons occupy earlier in ns orbitals than n-1 d orbitals due to their quantum effects. The d orbitals have the higher angular quantum numbers, which is 2, than s orbitals, which has 0 angular quantum numbers. Right? So the general rule is following. Okay? Electrons occupy earlier in ns orbitals than n-1 d orbitals. You can maybe follow this arrow to generalize how the Bell principle apply. Right? So for the crypto gain, you need to fill all the electron argon, right? Ground state electronic configuration followed by 4s, 3d, and 4p orbitals. Okay? 다 아시는 내용이죠, 그렇죠? 이번 화학 때 배우는 내용인데 혹시 몰라서 가져와 봤습니다. And this is another quiz that maybe practice quiz you can solve by yourself and get back to home, right? You can provide the ground state electron configuration of these elements, right? Following the Aufbau principle and Hohn's rule, right? And Pauli exclusion principle, and so forth. 그렇죠? 다 하실 수 있죠, 그렇죠? Right, maybe you can answer the following question, the very fundamental question, why atoms are forming bonds. And thus far, right, we review, right, how electrons are distributed within an atom, right? And the point was the balanced electrons are very critical. Balanced electrons are dictating the nature of the chemical properties of a given element. Okay? The next question, which is also very important, right, is how this electron rearrange and formulate the chemical bonds. Right? And this can be answered by the old theory, okay, Lewis theory, which states that the atom becomes stable as its outer shell is either filled or contain 8 electrons. You guys heard about, right? The rule. Or it has no electron of higher energy, right? That's what Lewis theory is stressing about. From which you can maybe identify the tendency of the atoms, right? Losing electron or gaining electron. Right? So here are example of the lithium atom and sodium atom, right, which have one balanced electron, as we discussed in the periodic table, right? And these species, these elements, right, can lose the electron, right, to form an ion with filled outer shell, right? So that's why, right, lithium plus cation and sodium plus cations are happy, right, and tends to be, right, the ionic species. Right? So the lithium and sodium atoms, they can achieve field outer shell basically by losing their electron. Right? And these elements, right, have one balanced electron, and same tendency can be found with species having two balanced electrons as well. So the element here located in this columns, this periodic table, they tend to lose electron, one or two balanced electron basically, to get the noble gas configuration. Right? And they will be very stable. What about these species, the fluorine or chlorine, right? These guys can achieve, right, the field outer shell by gaining electron. So they are happy with, right, getting the electron. For instance, the fluorine has 7 valence electrons, but by gaining or adding 1 electron can satisfy the octet goal. Right? So in this case, the minus anion, this can fill the outer shell. Right? So elements that have 6 or 7 valence electrons show these tendencies. They tend to get electron to satisfy the octet. Okay, so here the element in this periodic table, right? They tend to gain electron again to get the noble gas configuration. Okay? What about hydrogen? Right? You have hydrogen here, right? The hydrogen atom is a special case, right? They can become a proton by losing the electron. And this is stable. Proton is also stable because its outer shell is completely empty. Right? But the hydrogen can also accept an electron to become the anion, called hydride anion. Right? This is also stable because its outer shell is empty. Okay? That's why proton and hydride is a relatively stable species can exist and can participate in varieties of the reactions. Okay? There is another way, right? You can satisfy the octet or achieve field outer shell by sharing the electron, right? And that's how the covalent bonding arrives, right? So here's an example of fluorine again, right? Each fluorine shares one of its 7 valence electron to form basically here the covalent bond by which each fluorine can be surrounded by 8 electrons. So octet goals can be whole for each case. About hydrogen, each hydrogen here share its balanced electron, formulate the covalent bond here by which hydrogen can be surrounded by 2 electrons having filled outer shell. Right? That's why H2 and F2 molecules are relatively stable and can exist. What about other elements? This is a typical element we will encounter a lot in the OChem course and of course your daily life, right? So nitrogen, carbon, and oxygen atom, right? They can also achieve field outer shell by sharing an electron. So you have oxygen, nitrogen, carbon here and there, right? And oxygen basically formulate 2 covalent bonds, right? With hydrogen to become water. You know, water is a very stable species. The chemical. What about ammonia? In nitrogen, formulate 3 covalent bonds with 3 hydrogen, right? So you have 3 covalent bonds between nitrogen and hydrogen. What about carbon? Carbon can formulate 4 covalent bonds with hydrogen, the 4 hydrogen, right? Here, there. Okay? This is the methane molecule, you know. Right? So you encounter or see a lot of covalent bond basically between carbon and nitrogen, between variety of carbons, and carbon and nitrogen, and carbon and oxygen, and so forth, right? And of course, right, for each right element, the center element here, oxygen, nitrogen, and carbon, you can notice that each is surrounded by 8 electrons, satisfying, right, the octet. And you can also, right, think about from the viewpoint of hydrogen, right? Hydrogen is also surrounded by 2 electrons. So everyone is having this molecule, right? Everyone achieve Wheeler shell by sharing electrons. 너무 쉽죠? 그죠? You can characterize covalent bonds, right? You can characterize the polarity of the given bond, right? Polar bond, non-polar bond, right? Non-polar covalent bond can arise between bonded atoms having same or similar electronegativities. So these are typical non-polar covalent bond you can think about. Right? The carbon-hydrogen bond, carbon-to-carbon bonds you will see a lot in organic molecules. These are basically non-polar. What about polar covalent bond? Right? The bond between atoms having different electronegativities has to be polar. Right? Hydrogen chloride, water, ammonia, right? These are all the typical examples having the polar covalent bonds, right? And you can, right, designate the partial charge of a given element here. So more electronegative ion basically pull the electron from the element who has the lower electronegativities, which means this chlorine moieties has higher electron densities, and proton or hydrogen moieties here having lower electron densities. That's why it has delta plus, and this chlorine moieties has delta minus, the first place. Okay. And with this polarity, you can designate the directionality of the dipole from positive to negative. This arrow indicate, right, the polarity directionality, right? Again, from positive to negative. Okay? So negative end of the bond can be visualized with this arrow notification. And you all know that oxygen and nitrogen, right, they have higher electronegativity than hydrogen. That's why it has delta minus, and hydrogen has delta plus for each case. Okay. And there are some rules of thumb, right? You can refer to maybe this table, the continuum of bond type from carbon to carbon to, right, maybe the ionic bond, potassium cation, and fluoride anion, right? And the left-hand side regime is a non-polar covalent bond, right? The basic electrons are sharing almost equally in this extreme. And the right-hand side, you have ionic bond, right? For the ionic bond, electrons are not shared, right? Basically, the electron given by one element and the other element accept the electron. Right? Basically, the opposite charge attract each other. K plus, F minus, sodium plus, chloride anion, right? And there is some metric you can refer to, right? If the electronegativity difference is higher than 2, you can classify that bond has to be ionic, right? If the difference is below than maybe 0.7 or 8 or so, then you can characterize the bond as non-polar. In between, you can identify the polar covalent bond, right? The bond between nitrogen and hydrogen, oxygen and hydrogen, for instance, right? They can be classified as a polar covalent bond. Right? And here's an electronegativity table, right? Electronegativities of atypical or selected elements, right? And there's a trends, right? The atoms farther to the right, in the same row, right? Having higher electronegativities. Lithium, for instance, has 1, right, of the electronegativities. Fluorine has 4, you know. Okay? And atoms closer to the top, right? So within the same column, again, the closer to the top having the higher electronegativities, right? And you probably learned why this should be the case. The electronegativity trend correlate with the size of the element, right? So from left to right, from bottom to top, that's how the the electronegativities increase, right? Increasing trends follows. Okay, and if you refer to the number given, right, then you can calculate the difference, the delta, right, and then decide whether the bond between two elements are polar, non-polar, ionic, or covalent. Okay? So it's probably better to memorize, right, the electronegativities of this, right, selected elements, the typical elements, right. Hydrogen, for instance, 2.1, carbon is 2.5, right. The delta difference between, right, 2.1 and 2.5 is 0.4. That's why the bond between carbon and hydrogen is non-polar, right, in this formalism. Okay. What about the bond between oxygen and hydrogen? Its difference is around 1.4, right, higher than 0.7 or 8 or so, right. That's why the bond is polar. 그렇죠? 그래서 뭐 아주 typical한 엘리먼트 electronegativity 정도는 뭐 이미 외우고 계신 분들도 좀 계실 거고, 카본 2.5, 하이드로젠 뭐 2.1, 옥시젠 뭐 3.5, 나이트로젠 3.0 이 정도는 좀 알고 있어도 유용하겠죠. 그렇죠? And with the electronegativity trends and your ability to gauge the difference, right, the delta between two elements, the electronegativity difference, you can answer all these questions, right? You can decide which bond has to be more polar or non-polar, right? So you can maybe compute the difference between electronegativities or by intuition, right? You can answer the question as well. Okay? 어렵지 않죠? 그죠? And which of the following has the most polar bond and the least polar bond, right? Again, you can refer to the electronegativities of each element, right? Given for the given compound, and calculate the delta and compare its magnitude. So, right, for the polar covalent bonds, you can also think about the dipole, which is a vector, okay? Which has minus and plus ends, right? And this is how the dipole moment can be calculated. Dipole moment is a vector, right? And its magnitude can be decided by the magnitude of charge separation, the distance between these two charge, right? The size of charge times distance will give you the magnitude of the dipole. Right? So larger the charge separation and larger the distance, your dipole will have larger magnitude. Right? And this is the unit system for the dpi. Right? So basically, you can compute, right, the dipole moment from the length scale and the charge scale. Right? And this is typical example, the dipole moment for each bond, each given bond, the bond between carbon and hydrogen, this dipole moment is typically around 0.5 or 0.4. What about the bond between nitrogen and hydrogen? This is more polar, right? Nitrogen has higher electronegativities, right? So the dipole moment has to be larger. Carbon-carbon, it's a non-polar bond, right? Symmetrical case, dipole moment has to be 0, right? Carbon-nitrogen's around 0.2, carbon-oxygen around 0.7. Right? So basically, the greater the difference in electronegativities, the greater the dipole moment, right? And it's the charge separation getting larger. Okay? Yeah, so unit is called dpi, and this is how you can compute and calculate and how the unit system works. Okay. You can solve questions as well. Use the symbol delta plus, delta minus to show the directionality, the direction of the polarity of the indicated bond, right? So if you refer to the electronegativity table, then you can decide which one has higher electronegativities or lower electronegativities. For those have higher electronegativities, pulls an electron from what it belongs and having larger electron densities, right? And having delta minus. What about the bottom case, bottom problem? Determine the partial negative charge of the fluorine atom in a CF bond, right? And then bond information is given, right? The length scale is around here, and dipole moment is this much. So from the equation just defined for the dipole moment, you can calculate the partial negative charge of the fluorine atom. Okay? And here is a solution you can refer to. You can also visualize the electrostatic or electrostatic potential distribution. Right? So you can maybe notice here the reddish color, the red color, or bluish color, the blue color, right and left respectively. And red indicates electron reachiness or electron reach area for a given molecule. And blue color indicates electron deficiency or electron deficient area within the same molecule. Right? Here, lithium part has electron deficient area, and hydrogen part here formulate electron reachiness or electron reach area. Okay, so you can compare again the electronegativities of the elements and decide which one has to have the delta minus charge, or in other words, which element should pull the electron from where it belongs, right? So red color has the most negative electrostatic potential, meaning it has higher electron densities. In other words, it attracts the positive charge. Okay? What about HF molecule? You have very electronegative fluorine or F element here, right? That's why you have the electron reach area, delta minus, in other words, and delta plus area from the hydrogen. Okay? So bluish color has the most positive electrostatic potential. It attracts the negative charge. Okay? And neutral molecule have around greenish color. You can think about the molecular dipole moment. So thus far in the previous slide, you need think about the dipole moment of the bond on a given bond, right? The molecule may have three structures, right? And you can maybe encounter asymmetric case or symmetric case, right? For CO2, for instance, you know that the geometry of the molecule is symmetric, right? That's why the molecular dipole moment has to be zero, right? You have the more electronegative atoms left and right? So basically you have the opposite directionalities for two different dipole moment vector. And in sum, this will cancel out, and that's why you have zero dipole moment for a given molecule, right? So you should remember, right? The molecular dipole moment is the vector sum of all the dipole moment of a given bond that formulate the molecules. Okay, so carbon tetrachloride, again, this is completely asymmetrical, right? And for bonds, right, they will cancel out the net dipole moment. That's why it has the zero molecular dipole moment, right? These are symmetric case. What about asymmetric case? You have chloromethane, water, ammonia, right? And you can easily rationalize why these molecules have non-zero dipole moment. These are asymmetric, right? Meaning they have asymmetric bonds, and the sum of the dipole moment, the dipole vector for each bond will not be zero in this case. Okay? Right, I guess this is the last topic, the presentation of the organic compounds. Right? How you can represent the organic compound is quite important, right? You need to know how to describe the bonding nature, right? How molecule looks like. And one typical way is using the Lewis structure. So Lewis structures showing the non-bonding or lone pair electron, right? As dots. And also encompass the formal charge on atoms, right? If they have, right? You have water here, right? So in Lewis structure, again, you have this lone pair electrons, in other words, non-bonding electron. And there's a bonding electron, right? Present what a bond, right, notation here. And in water case, right, there's no formal charge. That's why you don't have any number. But for the hydrogen ion, right, you have now the plus notification here, indicating this oxygen now have one plus formal charge. Right? And this is how you can compute, right, or calculate the amount of formal charge. You can subtract, right, the number of lone pair electron plus half of number of bonding electron from the number of valence electron, right? That will give you the formal charge of a given element within the molecule. Right? Or in other words, right, you can subtract the number of lone pair electron and number of bonds, right, from the valence electron. That will give you the same formal charge, right? So you can maybe practice with the water, the same kind of stuff again. The oxygen, right? You're calculating here the formal charge of the oxygen within water, right? Its valence electron has to be 6. And you have number of lone pair, which is 4, right? And there are a number of bonds, which is 2, right? So 6 minus 6 will give you 0 formal charge. That's why the oxygen, its formal charge in water has formal charge of 0. You can do the same thing for the hydrogen ion, hydroxide ion, and hydrogen peroxide species, right? So for the hydrogen, right, again, oxygen have invariably balanced electron, right, of 6, right? And it has 2 lone pair and 3 bonds, right? So 6 minus 5 will give you 1. That's why the oxygen is plus 1. It's a formal charge. With the hydroxide anion, oxygen again, invariably having 6 valence electrons minus 6 lone pair, right? And 1 number of bond, right? So 6 minus 7 will give you minus 1. That's why oxygen here has minus 1 formal charge, okay? You can do the same thing for the nitrogen-centered molecule, okay? And here's a formula you can refer to as well. Okay? Again, from the 5 valence electron, invariably 5, right? You can compute the formal charge of all this nitrogen-containing compound, right? 어렵지 않죠, 그죠? 밸런스 일렉트론으로부터 lone pair 개수 빼기 본드 개수 주면은 formal charge가 나오겠죠, 그렇죠? You can do the same thing for the carbon-containing species. Carbon has valence electrons of 4, right? And again, you can subtract the number of bonds, number of lone pairs, electrons, right? And then you can rationalize why the formal charge of this central carbon has 0 plus 1 minus 1, 0, 0, respectively, right? For these cases. These are hydrogen species in 1 valence electron, right? And from each, right, you can rationalize why, right? Hydrogen ion, in this case, is plus 1 charge. Hydrogen anion is minus charge. And radical is, right, 0 formal charge in this case. Okay, halogen having 7 valence electron, and you can apply the same, right, formula to compute the formal charge of the bromide anion, which has to be equal to the net charge of a given species, of course, right? This is a practice you can try, and maybe you can check the answer next time, right? So you get each atom the correct formal charge, right? So you have all the elements, right, formulate this molecule. So you can compute the formal charge each element, right? Applying the same formula we just reviewed, okay? You can try that. the same thing here as well. 그래서 forward charge를 계산하시는 것부터는 조금 리뷰를 하셔야 돼요. 알겠죠? 왜냐면 이제 bond의 개수와 주어진 엘리먼트의 밸런스 일렉트론 대비 이 센트럴 애텀이 차지를 띄고 있냐 안 띄고 있냐 이거를 분별하는 거는 조금 중요합니다. 그래서 리뷰를 하시기 바랍니다. Okay. So computing the forward charge of the element within a given molecule is very, very fundamental and very critical and also very important, right? So you guys should be accurate on this, right? Because charge state dictate the reactivities and structure, sometimes structure the organic molecules. Okay. All right, I guess we can stop here, and maybe next time we can check the answer for the forward charge computation, and then we'll discuss a little bit more about the Lewis structure, and then we'll discuss Kepler structure, Condon structure, and how this can be used for describing the structure of organic compound, right? And then we'll keep discussing the molecular orbitals and hybridized orbital theories, and how this can be used for dictating and describing the bond within the organic molecule. Okay? 네, 여기까지 하고 다음 시간에 이어서 챕터 1 파트 마무리하고 챕터 2로 넘어갈 수 있을지 봅시다.